Okay, so we're going to find some one-sided limits given these four functions that you see. And then we're going to look at the graph and look at right-handed, left-handed limits. All right, so for question 2a, as x approaches 1, let's see, here are our options for this question. We want to answer with infinity, negative infinity, or if it's unbounded and it doesn't go the same direction, then we'll just write it does not exist, all right? So as I go to 1, so this is not a right-handed, left-handed limit. So I have to see if it goes to the same place from the right and to the left. So we're just doing this kind of numerical approach to see what happens as you get close to 1. So I just pick a number that's close to 1. And I see what happens. Okay, so what happens is you're in the bottom, you get a really small positive value and you square it and it's positive. So you're dividing by a very small positive. And up top, 2 minus somewhere close to 1 is also positive. Okay, so that was actually the limit as x approaches 1 from the right of this function. Okay, and we know that's going up. Now, if I let x equal be negative 0.99, then basically I'm taking the limit as x approaches 1 from the left of this function. Actually write it down this time. And is there any difference? And the answer is no, because if you put in 0.99 here, you do get a negative when you subtract, but when you square it, you end up with a plus. And then up top, 2 minus something close to 1 is always going to be plus. So this plus down here is really small, right? So you're dividing, that's the idea, you're dividing by a really small number. So they're both limits from both sides are going up to infinity. So we can say, we can do a little bit better than does not exist. We can say where it's gone. Okay, 2b, negative 3 from the right. Again, I'm just doing the same little numerical approach. We could approach it, right? Your textbook would do this. They would say, from the right of negative 3 is negative 2.9, and then you get closer, negative 2.99, and then you get even closer. So I'm saying pick any of these numbers, and we can kind of see what's happening. We know there's an asymptote here, right? So we know we're going to have this asymptotal behavior. So we just have to decide if it goes up or down. So if I take this value here that's really close to negative 3 coming in from the right, because it's slightly bigger than negative 3, then I end up with a positive on the bottom, very small positive. That gives me the asymptotal behavior where it goes up or down to infinity. And up top, I'm just trying to see if I get a positive or negative, right? In this case, I would get a negative value. So you have a negative constant up top, and then on the bottom, you have a number going to 0, but on the positive side. So that means negative, positive, you're going to negative infinity. Okay, so that's your answer for 2b. Over here, 3 from the right, so pick something a little bit bigger than 3, 3.1. So if you square 3.1, subtract 9, that's a very small positive number, right? And as you take the limit, as x approaches 3.1, your whole log function is approaching 0, right? This gets really close to 0, and you know that as you come into 0 from the right, that your function goes to negative infinity. Natural log function. 2e, 5 from the left, so that would be what, 4.9. So be careful here, you got a cube, so it's a little different. So I end up with a negative on the bottom. I cube it, I still get a negative, so I got a really small negative, right? Just something like that, really small negative on the bottom, and then e to some positive value. Yeah, that doesn't really matter. All we care that that's positive. You're dividing by a really small negative, so it's going to shoot down to negative infinity. Okay, let's do some limits based on a graph that we're given. Limit of this, so this function's f of x is piecewise defined function. As I come into 5 from the right, the function's down here at 0. Even though the output isn't 0, that's okay, but the limit is 0. As you approach 5 from the right, the graph approaches 0. As x approaches 1, so this is not a right-handed, left-handed limit, so you got to come both sides. As x goes to 1, what's your graph doing? It's going down to that hole in the graph that's equal to 2, even though the output's down here. Okay, negative 4 from the left, that'd be up here at 6. Coming to negative 4 from the left, you're up here at 6. coming to 3. Limit is f of x as x approaches 3. So this one's a little tricky. There's no dot there, but it's still an output on your graph. That's this line right here. So as you come into 3, my y value is up here. My y value is up here at 3. Okay. Let's see, and then one more as x approaches 5. We did the right-handed limit is 0. The left-handed limit will be up here at 4. So that means this one doesn't exist. The right hand doesn't equal the left hand. And f of 5, that's an old question, a pre-calculus question. Plug in 5, output right here. That would be equal to 4. Not continuous are your gaps in your graph. So you got x equals -4. You got x equals 1. And I'm just asking for the x values. You got x equals 5. 5 is non-removable, right? You got a serious situation here. You can't fill in a gap and make it continuous with just redefining one input and output. But you could do that with these other guys, right? These are more simpler discontinuities, if you will. So those we call removable.